Hello, everyone. How's everybody doing? Hopefully, you're doing fine. Today, we have another exciting day talking about nothing, absolutely nothing. So, if you've got nothing better to do and you want to talk about nothing, you came to the right place. I want to remind everyone before I begin on the subject of today that we have a conference. We have a conference in Sweden, Borås, Sweden, and that's going to take place on June 8th, 2019. It's a Saturday, and we're going to be discussing um, different subjects. Personally, I'm going to be discussing a subject very dear to me, and that is what is physics about? Essentially, what is science about? Um, I want to establish the foundations of physics. Specifically, I'm going to present a paper on what is a physical interpretation. And that's where we're lacking. What these people have been doing for the last 400 years, I say it's not physics. And you might say, well, you're crazy, Bill. You were saying ever since Newton, nobody's done physics. Essentially, no. And I can't say everybody. There's some people who were interested in reaching an understanding of how the universe works. But I would say at least since the beginning of the 20th century, that all died. It died because people started getting more into mathematical abstractions, and they left behind what we were supposed to do in the first place, which is figure out how this universe works. And so the question is whether someone who tells you that he moved a concept, does that qualify as physics? Someone comes to you and says, look, I can tell you how that mountain moved. Oh, okay. How did it move? Well, you see, there's this love, and love came in against the surface and pushed the mountain. And you say, love? What do you mean, love? And the guy said, yeah, love came in and pushed the mountain, moved it over. Well, the question is whether that amounts to physics. And especially when the person cannot define what he means by love. And specifically, if he can't tell you whether love is a physical object. I mean, if he said, look, the heart pushed the mountain, okay, we can all say, okay, yeah, surface came against surface, I can understand it. But when someone says an abstract concept like love moves a mountain, well, then you got to wonder about his state of mind and whether you should maybe, seek some help for him, okay? And I think that pretty much summarizes that little example where we stand today. We have all these concepts. We have fields, we have time, energy, mass, force, charge, we have wave. We have all these concepts, and they're moving around and making them clash and doing all sorts of things. And the question is whether any of that qualifies as science, let alone as physics. And I'm saying it doesn't. You need to do physics with physical objects first, and second, you need to have uh, um, you need to have physical objects, and you need to be able to make a movie of your theory because physics is literal. And by literal, I don't mean the words necessarily. I mean that what you show on the screen is is the mechanism that you're proposing for all these invisible workings of the universe. Oh, how Mother Nature runs her invisible shop. How does she do light? How does she do magnetism? How does she do gravity? These invisible mechanisms. That's what you have to explain. And we have no explanation for any of them coming from the mathematical establishment. So what they're doing, they call themselves mathematical physicists. Well, that word physicist doesn't belong in there. They could be mathematical, but they're not physicists. Okay, so that's in a nutshell what I'm going to be presenting. I'm going to, of course, go into a lot deeper than what I'm saying here. This is just kind of like the executive summary. Okay, so you get an idea. Uh, Living Bridge. Martin, I don't know what that's all about, but maybe you'll clarify that for me someday over a couple beers in Sweden. Anyways, let me continue here. For the last couple weeks, I've been dealing with the subject of nothing, nothingness, and the subject of ether, and the subject of infinity. And they all really go together. Um, what are we interested? What is a curious person, an intellectual interested in finding out? What really piques our interest? Well, we want to know what this universe is about. What is this universe? Well, where are we? Where are we, or what is it that we're in? You know, that sort of question. What is this universe? That's the question. And in order to answer that, you need to get to, is the universe made of something? I think that's a valid initial question, that you can ask. Is the universe made of something? And we can safely say that the matter out there, the galaxies, stars, gases, atoms, molecules, all that stuff, we pretty much understand, I think. In a sense, we can relate to it. We can say, okay, I know what a star is. A star is a shiny thing that's out there and it's made of atoms. I mean, I think that's like something very basic. If you don't go beyond that, at least you got a good notion of what a star is. So we have no problem with the matter part of the equation of the word universe. We have a problem with the other part, the space part. What is that black stuff, that dark stuff that is between the Earth and the Moon? That's where we're having a problem, a major problem, and a problem that people have not been able to overcome. That's the issue. The issue is that we don't know what that dark stuff is, or people have different ideas about it, or they use things which they introduce things into their theories which they have not justified. That's the overall picture of today. Okay, so in order to get a handle on this, I said, well, where do we start? Well, I started the discussion saying that relativists, well, really mathematical physics in general, both relatives and quantum mechanics, they say that the universe is made, space is made of something. And they start saying that the universe came from nothing. They tell you that vacuum is nothing. That's how they start their discussion or their debate or their dissertation. And then they immediately start putting things in that space and saying that, well, space is not really nothing. So they start by saying, look, space is nothing. And then they say, well, space is not really nothing. So what is space? Well, space is this stuff out there that we can't see, but we can see activity, or we detect, we measure, we are able to, in the lab, detect activity in space, in empty space, in vacuum. And that activity is diversely called, they could be called energy. It could be called virtual particles popping in from the void. There's all this sizzling stuff going on there. There are fields in there. So we have, virtual particles, fields, energy. All this stuff is in that space. In fact, they even say that space itself has mass because energy is another form of mass. And so if it has energy, well, then it's also got mass, right? So it's got all this stuff in there, all hidden in this vibrating space that we have around us. And the question is whether that's an accurate picture of reality. Is that how Mother Nature runs her universe? She has space being made of some vague things that we can't put our finger on, but it is truly made of things. And that's just primarily the quantum side, but the relativity side, which is the other half of mathematical physics, there's a little bit here for string theory, but nobody gives too much of a damn about string theory because it's just pure math. But relativity has a similar idea. It says, look, think of space or space-time as, some kind of fabric. That's the word they use, fabric. Okay, so you're supposed to think of this thing as a continuous whatever. I'll call it whatever because we can't really figure it out, right? And you can think of it as fields also, continuous fields. That's the word they like to use, fields, because why? Because fields has never been defined. So they say, yeah, it's a bunch of fields, or they'll say it's a bunch of energy. Okay, great. So in either case, whether you go to general relativity, you go to quantum mechanics, you're talking about space being something. The mathematical physicists have not come up with nothing. They have no idea what nothing is, and so they eliminated it completely. They have no use for nothing, especially in their equations. They can't put nothing in there. They have to put something, some value, some unit, some number, something. You can't say, look, it's nothing, because even zero for them is something. Zero is simply a plus one, minus one. That's what a zero is. So the zero, it has two components, and they're opposite in sign, and when they add up to zero. That's what you have to think about when you think of zero. Zero is not zero, nothing. It's you can think of it as black meeting white and becoming nothing. And then you separate nothing into black and white, or red and blue, or green and yellow, whatever colors you can think of. So zero is not nothing. Okay, zero simply means there was a transaction, a positive number minus a negative number, and you get nothing. So even in that case, there's no such thing as nothing. And so the question that comes up is, the first one is space nothing? And if it is something, what is it? What is this something of which space is? And, mathematical physics doesn't like the word ether. It's like Laughlin Nobel Prize said, it's taboo to speak that word, a word which I shall not speak, ether. But what is ether? Ether, traditionally at least, has been a whole bunch of particles. Just think of gazillions and gazillions of particles. And that body of particles, that's the ether. Okay, so that's it. That's the ether. And it takes no more science than that. And so they don't like to use the word ether, but that's what they're alluding to. And that also applies, by the way, to general relativity, because in relativity, an event is a point in space-time. Space-time is made of countless events, and each event is a point. What is a point? Well, you got to think of it as a little dot. You might think of it as a two-dimensional dot or as a three-dimensional ball, right, or sphere. But that's what that event is. It's something that happened at a given point in time. And so even space-time, the fabric of space-time is made out of all these particles called dots or points or events. So whether you talk about general relativity or quantum mechanics or even string theory, what is string theory trying to do? It's trying to unite general relativity with quantum mechanics. And what does that mean? It means that they're trying to interpret the equations of general relativity, which are based on the field concept, continuous structures, together with the point particles of quantum mechanics. They're trying to quantize space-time. Okay, I hope you understand that. They're trying to say, what is this little thing that's happening here in space-time? Well, for that, we need to bring quantum equations, and let's look at it with Schrodinger's equation or whatever. Okay, so they're trying to bring the equations of quantum mechanics into general relativity to try to unite that, and that's what has become string theory, an attempt to unify, especially gravitationally, right? General relativity with quantum mechanics. Right now, these two groups are not talking to each other. They hate each other, or they're not. They have no common ground. Okay. In fact, here you have the in quantum mechanics, you have the gravitons, discrete particles doing all the work, or that's the theory because it's a particle theory. And here you have a continuous structure called space-time, which is supposed to be some kind of, you saw the trampoline or fishnet analogy. It's supposed to be a continuous structure which you bend over, and, with a planet or a star or whatever, and that causes gravity. So here's the world of the big, and here's the world of the small. And they're trying to unite those. Okay. So that's one issue. What is the universe made out of, or made of? Okay, that's one part of it. The other issue is it infinite? Whether you're talking about nothing or nothingness, emptiness, space, whatever word you want to use there, void, zip, zero, fine, or whether you're talking about ether, false vacuum, canvas, the space-time canvas, whatever you want to talk about, I don't care. Whether you talk about that somethingness or that nothingness, is it infinite or is it finite? And if it's finite, what continues? And keep in mind that, you have people like Lawrence Krauss who had to redefine the word universe. Universe is no longer in their minds, space and matter, because that's not practical. It's not pragmatic. It's not an operational definition or a functional definition. An operational definition is to say, well, what do we need in real life? Well, I can't see that galaxy that's over there. It's beyond our field of view. It's beyond even interaction with our galaxy. It's so far away that we're going to consider that a different universe. It's a different universe not because it shares the same space. Yeah, I mean, it does share the same space as we do. It's a different universe simply because it's outside of our range of influence in either direction. We don't influence them. They can't influence us. We can't see them anymore. They can't see us anymore. But we all started from the same Big Bang, exploded, got farther away. That's in general the theory, right? And they're so far away that for practical purposes, we can consider them as a different universe. That's how they used the new word universe, because they had no way of reconciling the word space. If that universe, if that blob of matter is in the same space as our blob of matter here in the Milky Way, then we're part of the same universe because we share the same space. But it is that space that's causing the big problem. Since they can't define it, since they have not had, they can't zero in on what this thing space is, they say, well, I've got a solution. We'll just call anything we can't see, anything we can't interact with, we'll call that a different universe. So they had to redefine the word universe. Keep that in mind, because that's going to be very confusing in the future when you listen to these people. They'll talk about the word universe, and you'll say, oh, I thought Andromeda was in the same universe as we were. And they'll say, well, no, see, Andromeda is now so far away we can't even see it, can't interact with it, so we'll just consider Andromeda a different universe. Keep that in mind. That's the way they're headed. And that's only because they have no idea what space is. That's the problem. The problem comes down to that. So the question is, again, if space is a physical object, or if space is absolutely nothing, whatever you can think of as absolutely nothing, are either one of those two infinite, or are they finite? If they are finite, what continues? These are the questions we need to answer. That's what a physicist needs to answer. So before you tell me about your theory about light, gravity, whatever, no, let's fix space. We need to figure out what this thing space is. We need to get a handle on space. And if you're going to say ether, no problem. No problem. Say ether. If you're going to say ether, just tell me, because this is what I want to know before you tell me your theory. I don't want to hear your theory until I hear this first. I need to know what that ether is. What specifically am I talking about? Well, here we have a case. Where is it here? Is this the ether? Is the ether just a whole bunch of particles? Is that what we're talking about? Is that the ether? And so this is what we need to figure out. We need to figure out if we're just talking about a whole bunch of particles. So anyone who's got a theory and wants to talk about ether, I have no problem. Just answer to me if ether is just a whole bunch of particles. Okay, and it's a yes or no question. You either say, yeah, the ether is just a whole bunch of particles, and I'm going to start doing my theory based on that assumption. Okay, but then we have a little bit more problem before I can hear or listen to your theory. And the next problem we need to solve is whether the particles sit in space or whether space itself is all these particles. Is the word ether a synonym of the word space? Is space and ether the same thing? Or is ether something that's contained within space? Are these particles contained within something called space, something or nothing called space? Or is the ether exactly the same thing as space? Is space made of particles? I need to have that question answered as well. I need to know if you're talking about ether being something separate or something equal to space. And here I have a little picture to show you what I'm talking about. Here we have space, the first case, right? The one above says space is the same thing as ether. Okay? So we have a little fishbowl there, but the fishbowl and the water are both the same thing. And in the bottom scenario, space is a container that contains ether. Okay? And ether would be the water in this case. You put it inside space, and you end up with a fishbowl, which is a fishbowl containing that water. In other words, you have the space containing the ether. So which is true? Which is your proposal if you're going to propose the ether? Is space equal to the ether? Are they synonyms? Or is ether something separate than space, and space is some kind of container that contains ether, a bunch of particles, so-called, right? And then a question again that you would have there to answer is whether space is finite and whether it's something outside of space. Okay, these are the questions you would need to resolve before we can even listen to your theory, because you need to fix that problem first so we can follow your discussion. Okay, those things absolutely are mandatory. Okay. If space contains the particles of ether, if space is a container and the particles of ether just occupy space, you got a little problem to solve before you can continue also and tell us your theory. It looks something like this. If I can get it up there, let's see, there we go. Here you have all these ether particles, the red ones. The question, what is the white stuff that gives contour or which encapsulates them? What gives the particles shape? If the particles are ether and they're contained within space, space is the white stuff. So you have to tell me what that white stuff is. You can't just say it's space. Well, yeah, that's what we're trying to figure out. What is that space? Then you have to define what that is, or tell me if it's a physical object, you have to draw it for me and show me what contours that white stuff. Okay, one of the two. So we have to get these things fixed before we can listen to your theory. That's all I'm trying to say here, okay? You can't just go in there and say, oh, let me tell you my ether theory. I don't want to hear it. I'm not even going to listen to it. I want this solved first. You need to tell me whether ether is the same thing as space, whether ether is contained within space, and if it's contained within space, then clearly space is contouring each particle, and you still have to tell me what space is and whether space is infinite. If, on the other hand, space is equal to the particles, space is made out of particles, you still have the problem telling me how is each particle contoured. So you can't get away from that problem, and you can't get away from the problem of infinity. Is that whole body of particles infinite? And what do you mean by that? I mean, what does it mean? It means that if I walk to the end of the universe, what do I find there? There's no end to the universe? You see the problem where we have a problem, especially if you're going to treat space as a physical object. You're going to have to show me the shape of space. And you can't say, well, I don't know what it looks like because I've never been out there. I don't have the bird's eye view of God looking at, the universe out there. This is not a question of seeing or touching. This is not a question of experiment or of measurement. This is a question of conceptualization. You have to conceptualize it. Okay? You have to conceptualize for me what you have in mind. Does space have a shape and all the particles are within this space? And there's something outside of it? And if there's nothing outside of it, what do you mean by nothing? I mean, how is that nothing different than space? And all these questions are valid. And you need to resolve them. See, this is the smart people from WMAP, right? And they've come up with these ideas. And they said, look, the universe is made of particles. And there's your ether. All these particles are moving around, okay? And these are the heat measurements that they've made and they've mapped. Okay, great. So we have all this, and what do we have everywhere in the universe? What they're implying, there's all kinds of particles. Okay, so does the universe end where that oval ends? And that black stuff, what is that stuff? Is that nothing? And how is that nothing different than what's between those particles? Okay, so this is the issue. The issue is that they draw these ridiculous pictures where they show some black stuff outside of our universe, and the question is, what is that black stuff? They had to give it shape, and so they say, well, what you're staring at is the visible universe, the detectable universe. And that goes back to what I said earlier about people like Krauss now saying, well, the universe is really what we can see or what we can measure. Anything outside of that, we're just going to consider as a separate universe, even though shares the same space. And the problem there is that black stuff. That's the problem. The black stuff, they cannot identify it. And so they said, look, just anything outside our field of view is going to be a different universe. See how they get around that problem? So the changing of the definition of the word universe, or the notion we've had of the word universe, that's key now. It's going to become key because now they're going to say, well, we're just going to look at what we can measure. And that's what WMAP has done. But then they end up with this ridiculous picture of, this oval, and that's the visible universe. Anything outside of that, we'll just call another universe or whatever. Okay, they'll just say that because they can't tell you what that black stuff is. That's the issue. And they can't tell you how different that black stuff is from the black stuff that's between the Earth and the Moon. That black stuff is the same as the black stuff that's outside the last galaxy we can see. So there is no difference. And they're saying, well, what we have here is ocean. What we have over there is air. That's what they're saying in a sense. They're saying that space out there is different than the space here. That's essentially what they're saying. And again, they don't have to define, what this stuff is. Okay, so when you push them a little further, they end up saying, what these particles are. And you say, well, what are those particles? I mean, what are they? And this is what they give you. They give you this notion that particles are really vibrating fields. Okay, so you have all these little particles in the field. Each one has a field that extends to the edge of the universe. That's how they conceptualize these things. And so, Then you ask the question, what is a field? And that's where it all ends. The buck stops there. You cannot figure out what a field is, and that's convenient for them because we don't know what a field is. Oh, okay, we're done. Particle is a vibrating field, but we don't know what a field is, so we've got it made. We're done. We identified the particle. That's as far as we got. We don't know what a field is. Some magical stuff that Faraday invented. That's where it all stopped. Okay, so one issue is, what is the universe made of? The other one is whether it's finite or infinite. Okay, and this traditional universe we always thought of, as being infinite. And again, the relativists, people who work on these projects, they say no, they hint that it's finite. What are they talking about? They're saying that black stuff on the right picture, on the picture on the right, is different than the blue stuff between the galaxies and matter on the inside of the oval. That's essentially what they're saying. Okay, so these people are just telling you in so many words that there's a difference between the universe that you've been educated to believe in, which is this infinite universe, and a finite universe that they're coming up with these days. Okay. So, is the universe finite or infinite? And relativists especially, they have perfect answer for it. It's both. The universe is both finite and infinite. And you say, well, hold it, how can that be? It's either finite or infinite. No, it's both. It's both. And how do they explain that? Well, they had to come up with some fancy footwork. They speak in tongues. And it goes something like this, the argument, right? The universe is finite, because it's like the Earth. The Earth is finite, right? Essentially, the Earth has a surface, right? And it extends to that surface. So it's got an encapsulating surface. How is it infinite? Well, it's infinite because it's unbounded. And what they mean by this is that you can walk forever around the Earth, for example, right? And never find, a fence. You will never find something that stops you. It's finite but unbounded. And what they're really talking about is walking incessantly. They're talking about two different things. They're saying, look, in one case, they're talking about structure, and the other one, they're talking about verbs, about motion. Okay? So this is the issue. The issue is that these people are cheating. They're cheating. They're just doing word wizardry. That's what it amounts to. Okay? They're saying, look, you can walk around it, and we'll call that unbounded or infinite because you can walk infinitely around it. And why is it finite? Oh, it's finite. It's easy because it's an object, and all objects have a finite extent. You see how they do it? And that's how the universe is both finite and infinite. In fact, Stephen Hawking explains it in his book. He says, the universe, referring to space-time, you could walk all around it and eventually come back to your starting point. And that's how they explain the infinite part, the unbounded part. Okay. Here's another notion of the infinite finite, and that is what I showed last week, what the Greeks had. The question that they debated was the same as today. Is the universe contained within a cylinder, like in this case, or does the ether contain, Mount Olympus as well? Does it contain the dwelling of the gods as well as everything else? So this is something that the Greeks already debated 2,000 years ago. As you can see, no one has solved the problem. What the answer is today is that these people would give the Greeks is it's both. It's both infinite and finite. And then they would go on with their little explanation of how it can be both. Real quickly, I went through the different schools of thought. And there were more schools in this, but these essentially summarize the different views. We have the Eleatics on the upper left, and they said there's no motion in the universe. The whole universe is filled with ether, but there's no motion. How do they justify that? Well, they said you can't have motion because there's no such thing as nothing. And if there's no such thing as nothing, anything that would move into nothing simply ceases to exist. So therefore, there can't be motion because motion would imply that things go into non-existence. That was their reasoning. The people from Abdera, such as Democritus, he said, look, there's only atoms and empty space. Essentially, he was giving you an ether theory. He did not address, as far as I know, he did not address the issue of whether it was infinite. I guess he did believe that it was infinite, space being infinite and all these particles just being somewhere in space. We don't have much information from Democritus beyond that. Aristotle, he took this and he says, look, we have the ether, but there is motion. But the motion is in such a way that particles simply move to where another particle was. So if there's an air particle or a water particle, as soon as one moves, the other one takes its place. So unlike the Eleatics, they said there is motion, but the motion is because one leaves space to the other. Okay, and the only difference with the Stoics, who came slightly later than Aristotle, is that they said that there's some kind of divine substance outside of the ether. Okay, so there's ether, there's air, earth, water, and which one am I missing? And fire, and beyond the ether, you have some kind of substance that they couldn't put their finger on, but they just hypothesized it. Okay, and here is a way of visualizing what these schools, the main points of these schools. In the case of Democritus, he says a particle moves into empty space. Parmenides and the Eleatics, they said, look, there is no motion whatsoever. And Aristotle says, well, there is motion, but see, there is no empty space. What happens is one particle simply occupies the space of another particle. And the 15 square puzzle is a good analogy for what these people were trying to say. Okay. So what happened was that for the next maybe 1500 years, the ether was identified with the soul. They took it more into religion and less into physics or mathematics and all that stuff. They got to the point where they said, look, if you get sick, it's because you have these bad vibes coming from the stars, and that's the ether that's penetrated your body. So the ether was really identified more with the soul. That went on for many years, at least 1500 years, what we call the Dark Ages, the Middle Ages, all this in a region. People were not too much into doing things scientifically or thinking in scientific terms. There was a lot of astrology, a lot of alchemy being done, and all these things were kind of mixed. So no real thing of importance comes out of that other than for historical reasons, what these people did and thought, etc. But nothing new really developed out of what happened those 1500 years. It's not going to be until the early 17th century. I would say Descartes is an important person. René Descartes. He kind of brings the ether back to life, and he tries to analyze it. Why does he have to analyze it? Well, for the same reason, I guess, that Galileo tried to analyze it. They tried to figure out, light. They were concerned about light. One of the issues was whether light travels instantaneously. And they said, well, Galileo ran an experiment mountain to mountain. One guy uncovers his lantern, says, as soon as I uncover mine, you uncover yours. And they did. And as fast as they wanted to do it, the transmission was instantaneous. So Galileo concluded that light was instantaneous. Descartes takes that. He was in communication with Galileo. He says, okay, light appears to have no speed. It's instantaneous. Okay, and based on that, he says, well, what is it that light is? and they brought the ether back in. They said, well, ether, the light is simply particles of ether that hit my eyes. You know, already the idea had come from Alhazen. He was an Arab scholar, and a whole bunch of scholars of the 10th, 11th, I think even up to the 12th century. And they talked about light. They did a lot of experiments on light. They figured out angles and that kind of thing. And they had this idea that light, comes from the object and reaches the eye. Until then, most people believed that it was the eye that threw particles at the object, and that's how we saw things. And if the thing was too far away, well, the particle never reached there. That's how they visualized it. Alhazen and his Arabs, they bring that back and they say, no, really, it's the other way around. The thing is sending particles to your eye. They like that idea better. And Descartes, by the 17th century, he starts thinking, well, it's all these particles of ether. They're the go-betweens. They are the mediators of light. Okay, and he visualized them as particles. So this lasted until the mid 17th century, and then one of the things that happens is Romer, he discovers that light does have a speed. Christian Huygens, Holland, he's going to calculate that speed a little slightly lower than the actual speed it has, but they started to realize that the speed of light is finite. And based on that, they said, well, what is it that is coming towards us? And again, there was this debate between particles and something new that had been introduced, I say, by Robert Hooke, and that is the wave. They started, and that came out again in 1665 in Hooke's book Micrographia. In 1665, he starts talking about light in terms of waves. And, by that time, or a little later from that time, Romer discovers that light has a finite speed. Huygens takes both those ideas and he writes his book, 1690, Treatise on Light. He's the first guy to treat it. He's considered the first mathematical physicist, by the way. And he treats these two things, and he treats them under the notion of waves. That's how the wave comes into being, essentially. It comes from a couple guys who, these ideas were floating around. They were waving around, and finally Huygens says, let's make sense of all this. He writes his book, and he's got a difference with Newton. And let me show that first. The idea we have today is that Christian Huygens was a wave theorist. And he says, look, light propagates in waves, so we got to think of the ether as being the vibration of waves. And Isaac Newton saw as particles, and he says, no, look, all these, the ether is made of particles, or whatever's out there, is, especially light, is mediated by particles. Okay, this is the notion we have today. And I say that this notion is really wrong. It's not really what these people were saying. And I disagree with a lot of the people who write about the debate between Huygens and Newton, because that's not the essence. That's not what was being debated between them. Let's get it straight. Both Newton and Huygens both believed in particles. Both of them thought that the ether was made of particles. In the case of Huygens, he thought the particles were vibrating. In the case of Newton, Newton says things travel straight. What was the issue? The issue was that Huygens believed that, you have this either longitudinal waves or spherical waves. He described them as spherical waves. And initially he said, look, they're spherical waves, much like sound, that from where you make the sound, everything just travels radially. And in his book, he goes and describes in more detail how a stone falling into the water creates these wavelets. And he explained that process. He said, how secondary waves are created. And he says each point in a wavefront is a source of a new wavefront. So it's circles being created by circles, and so on. And that's how a wave expands. So he's got two analogies, one sound and the other one water. Okay, he uses these two examples to try to figure out how to describe light. Okay, and again, he's basing his ideas on what Hooke had said and on the fact that we have Mr. Romer deciding or figuring out that light had a finite speed. And, in fact, Huygens is going to calculate that speed and going to put it in his book. Okay, so what's the issue? The issue is that Huygens has this idea. He says, this is from his book, right, 1690. And he says, the successive movement of light being confirmed in this way, it follows, as I have said, that it spreads by spherical waves. Okay, so he's talking about spherical waves, and he's talking about the movement of sound, which is longitudinal, remember that. But at the same time, he's talking about particles of the ether. Okay, where's the problem? Where's the fight with Newton? Well, he says that right up there at the bottom, he says, they're structured to assume such a disposition as to give this fluid matter the most overt and easy passage possible. In other words, Christian Huygens saw the ether as fluid. Think of it as either air or as water. So that's what he's thinking that ether is. He's saying it's made of particles, and I guess he also believed that both air and water were made of particles. So he said, look, the ether is also made of particles. It's some kind of fluid like air, like water. And I guess he believed that was fluid because it went through our bodies. It went through solid things. So it had to be some kind of fluid that could get into a body. I guess that's how he visualized it. And he says this fluid matter vibrates. Okay? So that's why he's talking about waves. He says that the fluid matter vibrates. Those are the waves he's talking about. Okay? Where's the fight with Newton? Well, Newton said, let me get it here. So I hope you get the Huygens version. His version is, the ether is a fluid. Keep that in mind. It's a fluid. What do we mean by that? He's using as an analogy. He's using air and he's using as an analogy water. These are fluids. They move. The one's a gas, the other one's water. But as far as he was concerned, these are all made of particles. And he thought also that the ether was made of particles. So he's not, people say, well, he was a wave guy. Yeah, a wave guy, but we have to understand what that means in Huygens' mind. He's saying, look, it is a wave, but it's a wave of particles. The particles are vibrating, okay? And what does Newton says? He says two things. He says, you got two things wrong, Huygens. The first one is the medium. And the second one is straightness. Okay? They both believed the ether existed. They both believed that the ether was made of particles. Both Newton was a particle guy and Huygens was a particle guy. They were both particle guys. Okay? Let's get that straight. This guy is saying the particles vibrate up and down and the medium has to be fluid for it to do so. Newton says, you're wrong. You're wrong because the particles travel straight and it cannot be a fluid. It's got to be a solid. Okay? It's got to be a solid for that wave to go through. So the issue was not particles versus waves, in a sense. The issue was the medium and straightness. We got that? Okay? So here's Newton. If I can get him right here. Here's Newton. He says, look, I'm not going to read all of this. You can find it in his treatise on optics, right? He writes the treatise in 1704. The first paragraph on the right, on the top, it's from 1672. But you can see that he hasn't changed one bit from 1672 to 1704 when his book on optics was published for the first time. Okay, and above he says, like the rays of light, be propagated in straight lines without a continual and very extravagant spreading and bending every way into the quiescent medium. In other words, Newton said, if you have a fluid, you cannot have straight propagation of light rays. That was his first issue, okay? And again, he says that at the bottom. For pressure and or motion cannot be propagated in a fluid in right lines, meaning straight lines, right? So Newton was saying, look, we got a problem. If you have a fluid, you cannot have straight propagation of light. Okay, that was the issue. And so let me give you the law, because we've shown this through experience in the lab. You can send torsion waves. Someone mentioned this. That's why I want to clarify this point as well. You can send torsion waves. Take a rope, put it underwater, and you'll send that torsion right through the rope. No problem. You just torque the rope, and water has no effect whatsoever on that rope. Okay, you can send torsion waves through the water. Okay, can you send sound through the water? Yes, you can send sound through the water. Okay, whether you can torque the water, yeah, I guess you can torque the water as well without a rope. You've seen helical motion inside the water. I should have brought something to show you, but I'm sure you've seen something like that in your lives. There are what we'll call vortex, right? Vortices, and you can have vortices in water. What you cannot have in water, this is the point that a lot of people miss. You cannot have transverse waves in water. You can have longitudinal waves, okay? You can have torsion waves, one-dimensional, three-dimensional, just to use that nomenclature, that way of speaking. You cannot have transverse waves in water. What is a transverse wave? A transverse wave means that here's the light or whatever going in, the wave itself is going in a straight line in direction, here it will be from right to left, okay? Right to left. We're moving right to left. Transverse means that it's waving up and down, perpendicular to the direction of motion. That's what transverse means. You cannot have that type of wave in water. You cannot have transverse wave in water. You can only have it in steel. You have a steel beam, then you can have it. You can have vibrations. In fact, we have transverse waves during earthquakes. We have both longitudinal and transverse waves because you're talking about a solid. You're talking about, the ground. You're talking about the earth. So you can have both transverse and longitudinal waves in the middle, inside, in the body of the earth. See, you can also have longitudinal transverse waves on the surface of water, which in fact, I think I have it here somewhere. Here. You can have transverse and longitudinal waves on the surface, but currents, you cannot have transverse waves. That's the issue. Okay, you cannot have transverse waves in the body, in the three-dimensional volume of water. You can have it only in the two-dimensional surface of water. That's the point, okay? So what are we saying? We're saying that Newton was right about this in this sense. He's saying, look, he didn't know anything about transverse waves. Neither one of them knew about transverse waves. They only were thinking of longitudinal waves. But to Newton, it was against his intuition that you could send waves through the ether, transverse waves. And again, he was thinking of vibrations, right? So he was thinking in terms of transverse waves, whether he knew it or not. He was saying you can't have this kind of thing in a fluid. You need to have a solid. And so he explained it in different terms. He said, look, there's a difference in density of the ether inside a body versus what's outside a body. In other words, the density, you could say, in air. So the density of the ether in air was different than the density of ether in steel beam. And he says, well, when they meet, that's where the clash starts, because here this thing is coming like in a straight line, and then it reaches this solid thing and goes off and refracts. It doesn't continue straight like it should, right? That's what his idea was. And here I have, see if I can find it. These are, because you can always say, isn't this a matter of degrees of stiffness? And it is, in a way it is. And here I've made a little picture just to give you an idea how we can explain this pictorially. If you have a gas or if you have a liquid, the first two there, they have a certain stiffness, but their stiffness is much less, obviously, than a solid such as a steel beam. Okay? So you can send a transverse wave through a solid, but you cannot send a transverse wave through a liquid or a gas, as Newton said, because it's just going to go off. As soon as it goes up, what's going to stop it? What's going to make it vibrate downwards again? The transverse wave. And the only way you're going to get no vibration whatsoever is if the thing is made out of a single piece. Think of a perfect cube, just an ideal cube in your mind. There's no ideal cube out there, but think of an ideal cube. It's made out of a single piece. And you cannot have vibration in something that is made of a single piece. That's not made of parts. Steel beam is made of parts. It's made of atoms. That's why you can still send a transverse wave through a solid such as a steel beam. But when you get into water, you can't send a transverse, or gas, you can't send a transverse wave because it, what's going to send it back? What's going to make the wave come down or up? For example, let's see, I think I have another picture here. I think it's this one. Yeah. See, here you have two transverse waves, the typical electromagnetic wave, right? Well, you can have this type of wave go through a solid, but see those red arrows that go up? Those are vectors, by the way. Those are intense. They just give you a magnitude. That's what it is, magnitude and direction. That's what each one of those little arrows is. Why would it come back down? Why would the arrow, once it goes up, what prevents it physically from continuing up and up and up forever? And the answer is there's nothing there, and not in water, not in gas. The only way you can have it come back down is if you have something solid like steel or whatever, any solid. Then you can send a transverse wave. And that's essentially the criticism that Newton had against Huygens. Okay. Unfortunately, I'm out of time. I was hoping to cover a lot more today. I'm going to continue on Wednesday because I want to get into this 19th century Fresnel and the fight that started in the 19th century with the wave. Remember, the wave in the 19th century replaced Newton. They got rid of Newton altogether. Particle died in the 19th century, especially in 1821 when Fresnel, Augustin Fresnel, Frenchman, he had to explain polarization. He explains it with transverse waves. That's when the transverse wave is born, 1821. That's over 100 years after Newton and Huygens. So neither one of those two ever knew what a transverse wave was. But when we get into transverse wave, we got a little bit of a problem because we got the Newtonian problem, the one he identified. They have the ether, they have the transverse wave, but in order to propagate a transverse wave through the ether has to be made of steel. It cannot be a fluid. That's where the problem's going to be. Okay, so I'll see you again on Wednesday, and we're going to continue with this exciting topic of nothing and ether and infinity. We'll see you on Wednesday. Bye-bye.